Here is an observation. Let x1, x2 be a generic element of R2. Then we can write x1, x2 as the sum of x1, 0 plus 0x2, which in turn can be written as x1, the scalar product x1 and 1, 0, plus the scalar product x2 and 0, 1. So any element of R2 can be expressed as a linear combination of 1, 0 and 0, 1. For instance, 3, 11, which is in R2, is equal to 3 times 1, 0 plus 11 times 0, 1. Another instance, 7, negative 5 equals to 7, 1, 0 plus negative 5, 0, 1. Of course, we can just write minus if we want to. And so on. Any element in the space R2 can be expressed as a linear combination of the vectors 1, 0 and 0, 1. Similarly, in R3, all elements of R3 can be expressed as linear combinations of 1, 0, 0, 0, 1, 0, and 0, 0, 1. So let's write that down. So similarly, all elements of R3 can be expressed as linear combinations of 1, 0, 0, 0, 1, 0, and 0, 0, 1. So here's what we will take as an element of R3, something like x1, x2, x3. So we're going to get x1, the scalar product of x1 and 1, 0, 0, and then plus the scalar product of x2 and then 0, 1, 0, plus the scalar product of x3 and 0, 0, 1. We use some terminology to define this idea. So we use the terminology spanning set. So here is our terminology. So we use spanning set to describe any collection U1, U2, and so on up to K in a linear space V such that every element in the set V, so such that every element in set V in the space can be expressed as a linear combination of U1, U2, all the way up to UK. Okay, so we will say that the U1, U2, all the way up to UK is a spanning set of the linear space. Let's take a look at some more examples of spanning sets. So here is our definition. Let V be a linear space, a set U1, U2, U3, all the way up to UN in general, is said to span V or be a spanning set of V if and only if for every element V of the space, V is some linear combination of U1 all the way up to UN. That is, V equals C1 U1 plus C2 U2 plus C3 U3 plus and so on plus Cn UN for some scalars C1, C2, C3 all the way to Cn within the field of the linear space. Okay, so here we have some examples of spanning sets of R3, of the linear space R3. The one we did on the board, the one we presented on the board. E1, 1, 0, 0, E2, 0, 1, 0, E3, 0, 0, 1. Spans R3. That's because for any generic element of R3, that generic element can be expressed as a linear combination of our three elements, E1, E2, and E3. You want to use, you can use notation. This notation is pretty standard. These are called elementary vectors in R3. Second example. The collection consisting of 0, 1, 1, 1, 0, 1, 1, 1, 0 is a spanning set of R3. What we need to show, if we're asked to establish that this is a spanning set of R3, what we want to show is the following. We select a generic element of R3 and we write it as a linear combination of our given elements. The goal is to find suitable values of the coefficients of the scalars. In other words, we want to solve for C1, C2, and C3. When we find solutions, then we have established our collection is a spanning set. So let's try this example here. I'm clearing the board, and then we will work out the problem on the board. Okay, so we're taking, we're setting x1, x2, x3 equal to c1 times our first entry, our first element, which is 0, 1, 1, plus c2 times our second element, which is 1, 0, 1, plus c3 times 1, 1, 0. Okay, so we are solving for the coefficients. Basically, what we're doing is if we want to, we could solve for the coefficients, but really what we want to do is show that there is a solution. Show that you can express our given generic element of R3 as some linear combination of our three elements. So that means we're trying to show that there is a solution to this equation. So is there a solution to this equation? Notice that if we look at the augmented matrix that we would use to solve a system for C1, C2, and C3, that would be a square system. So it all boils down to finding out whether the system, that square system, has solutions. So here's my coefficient matrix. When I set up my associated system, my coefficient matrix, it's the matrix is 0, 1, 1, 1, 0, 1, 1, 1, 0. So we know how to check whether a square system is solvable from the coefficient matrix. If its determinant is different than 0, then there will be a unique solution. If the determinant equals 0, then there will be no solutions or infinitely many solutions. So we're not expecting infinitely many solutions here, of course, because this is a generic element of R3. So by finding the determinant, we will find there is a unique solution or there are no solutions in general, because this is a generic element. Okay, so what is the determinant in this case? Let's do our cofactor expansion along the first row. So we have 0, and then the determinant of 0, 1, 1, 0. This is of course 0, so we don't need to bother with that. Then minus 1, the determinant of the minor 1, 1, 1, 0, plus 1 times the determinant of the minor 1, 1, 0, 1. Okay, result. That's -1. The determinant of my first minor is -1. -1 times -1 is +1. And here I have plus 1 times the determinant of this last matrix, which is also 1. So we end up with 2. 2 is not equal to 0. So the associated square system that we use to solve for C1, C2, and C3 has a unique solution. Conclusion: there exist coefficients C1, C2, C3 in F, in R, that solve the system. Consequently, x1, x2, x3 can be expressed as a linear combination of our three given elements. Another one, the collection consisting of elements 1, 2, 3, 3, 2, 1, 2, 3, 1 is a spanning set of R3. Once again, here we have three elements in R3, and what we're doing is we're determining whether the associated system for solving to solve for C1, C2, C3 in the equation x1, x2, x3 equals to a linear combination of the three given elements. If we can show that there is a solution to that system, we are done with the question. Is there a solution to that equation? This leads to a square linear system. So if the coefficient matrix has determinant different than 0, there are solutions. Of course, we can expect to encounter cases where there are no solutions. So we have to look at an example like that also. So here we're trying to compute the determinant of 1, 2, 3, 3, 2, 1, 2, 3, 1. Let's double check here that we copied this correctly. 2, 3, 1. So 1, 2, 3, 3, 2, 1, 2, 3, 1. Okay, so there is a shortcut for finding determinants of 3 by 3 matrices. I'm going to take that shortcut here. I could use my cofactor expansion, but for 3 by 3 matrices there is a shortcut. It's well known. You extended your matrix with 2 columns, being the first column. I don't need to draw this, just the additional columns. So repeat the first column and repeat the second column. This is a rather common trick. It only works for 3 by 3 matrices. It doesn't work for 4 by 4 matrices, but we're going to try it because it works for 3 by 3 matrices. So first you multiply the diagonals, the main diagonals. 1 times 2 times 1, that's 2. 3 times 3 times 3 is 27. 2 times 2 times 1 is 4. You add those, so you get 2 plus 27 plus 4. Then you do the same with the reverse diagonals. So now I go to these 3 diagonals. I multiply each of them, so 3 times 2 times 2 is 12. 1 times 3 times 1 is 3. 1 times 2 times 3 is 6. And then what you do is you add them. So you say 12 plus 3 plus 6. But then you subtract the result from your previous sum. Okay, so let's see what we get from this. 2 plus 27 is 29, plus 4 is 33, minus 12 plus 3 is 15, plus 6 is 21. Whatever this is, it is not 0. So conclusion, the equation that we set up, x1, x2, x3 equals to c1, 1, 2, 3, plus c2, 3, 2, 1, plus c3, 2, 3, 1, will have solutions, C1, C2, and C3. I did not, the method I've used did not find those specific values for the coefficients C1, C2, C3. If you want those, if you actually want to find the coefficients, then Gaussian elimination is necessary. You have to set up your system of three equations with variables C1, C2, and C3, and then you will have to use Gaussian elimination to solve for C1, C2, and C3. In this presentation, we are going to forego that because the question is simply about whether there is some linear combination of your given elements that can express a generic element of this space. So we have no problem with using our theory of determinants to answer the question efficiently. Okay, here is a few more examples. We have to be brief in solving them. So this time we're working in the linear space R4. So determine whether the given collection of elements of R4 spans R4. So for number 1, we have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, so let's pick a generic element of R4. So let x1, x2, x3, x4 be elements of R4. Now, we're trying to determine whether I can write that generic element of R4 as a linear combination of 1, 0, 0, 0. So I'm putting a question mark there. 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And the answer in this case is yes, we can. And in fact, it is easy to tell what the coefficients have to be. So first I get x1. Here I have to get x2. And then x3. And then x4. So it is simple because of the fact that our given elements of R4 have only one non-zero entry. Notice that they are in different locations. It is possible to write every element of R4 as a linear combination of these four. Now, let's say that we were not given all four, that we were given only 3 of them. Then could you still write your generic element of R4 as a linear combination of just 3 of them? Let's say the first 3. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. In this case, you may suspect the answer is no, and it is easy to see why. When you actually perform the scalar products and then combine like terms, your first resulting entry is x1, then you get x2, then you get x3, but then in the very last one you get 0. So there is not going to be solutions to this equation whenever x4 is different than 0. In other words, I don't have freedom to select a generic element of R4 if I want to be able to write it as a linear combination of these 3. The last one will have to be 0, otherwise no solution. But that's not what we want. We're saying, here is a collection. Does it span this space? If you ask that question, does the collection span this space? The answer is no, because there are some elements of R4 that cannot be written as a linear combination of those 3. As long as you put something here different than 0, it is impossible. All right, let's do another one. So is the collection 1 1 0 0 0 1 1 0 0 0 1 1 1 0 0 1 a spanning set of R4. Okay, so let's see. Let's set up our our linear combination. Our linear combination in number 2. If we call the first entry U1, so if you call that first one U1, and U2, and U3, and U4, then what we get is that we want to determine whether there exists scalar C1 all the way up to C4 such that V equals to a linear combination of the linear combination C1 U1 plus C2 U2 plus C3 U3 plus C4 U4. Here V would have to be understood to be a generic element. Now, so notice that when we set up our system of linear equations to solve for C1, C2, C3, we get a square linear system. So in this case, we can check by just computing the determinant of the coefficient matrix. Coefficient matrix is easily formed by putting R4 elements of this space in columns of that augment of the coefficient matrix. Okay, so the calculation is somewhat tedious, but it turns out that the determinant of that coefficient matrix is 0. So there is no guarantee that we will be able to write a generic element of R4 as a linear combination of our 4 elements, U1 all the way up to U4. Now, to ratify that that's in fact the case, you need to display an instance of an element of R4 that cannot be written as a linear combination of U1, U2, U3, and U4. So sometimes you can pick your elements almost at random. So I decided here to pick this element of R4, 1, 1, 1, 0, and try to solve the system. So here is my augmented matrix. So I have my coefficient matrix, and then the element of R4 that I'm using in the hopes of showing that there will be no solution to our equation. So elementary row operations, it will reduce this augmented matrix into that reduced row echelon form matrix. As you can see, the last row is has 0, 0, 0, 0, negative 1. So that last row says 0, C1 plus 0, C2 plus 0, C3 plus 0, C4 equals negative 1. But you know that's just 0. So that last row is implying this equality, which is a false equality. It's an impossible condition. So we just conclude that the element 1, 1, 1, 0 of R4 cannot be written as a linear combination of our given elements of R4, U1, 1, 1, 0, 0, all the way up to U4 equals 1, 0, 0, 1. We cannot write this element of R4 as a linear combination of those elements. Consequently, the set U1, U2, U3, U4 is not a spanning set of R4. Okay, Another one, number 3. This will be the last one we'll try for this video. Determine whether the collection containing the 3 elements of R4 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0 constitutes a spanning set of R4. You may suspect that the answer is no. So, because it looks like when we try to set up our system of equations that we have some sort of a deficiency. Something is insufficient. So let's try it. So I want to form a linear combination of my given elements of R4. So here's my set. Here is my set. So U1, U2, U3. There are 3 elements in that set. So explicitly 0, 0, 0, 1. And then 0, 0, 1, 0. And then the last one is 0, 1, 0, 0. Okay, so that's the first one is going to be U1, the second one is going to be U2, the last one is going to be U3. So it looks like I cannot write it looks like I cannot write this fellow 1, 1, 1, 1. So 1, 1, 1 cannot be expressed as a linear combination of U1, U2, U3. Now, what's the problem here? The problem is that when you add C1, 0, 0, 0, 1 plus C2, 0, 0, 1, 0 plus C3 equals to 0, 1, 0, 0. When you add those, when you compute this linear combination, when you do your algebra, C1 0 plus C2 0 plus C3 0 is 0. And then you get C1, C2, excuse me, and you get C1, C2, C3. That's what you get. Now, if you equate that to your chosen element, 1, 1, 1, 1, you are saying that C1 equals 1, C2 equals 2, C3 equals 1, and 0 equals 1. That's a false statement. When you set 0 equals 1, excuse me, 1 equals 0, that's a false assertion. That is an impossible condition. So that means this equality cannot be satisfied. Consequently, our collection is not a spanning set of R4. Okay, so what's the problem? The problem is that we don't have enough elements in this set to be able to express any generic element of R4 as a linear combination of them. So here is what you probably realize is that to be able to be a spanning set of R4, you need at least 4 distinct elements in R4. This is too small a set. It has less than 4 elements. So that's a fact. If you look, you can think of Rn in general. Let n be a positive integer. It is impossible to span Rn with a collection of elements that consist of less than n elements. So that could be a remark. So let's put that as a remark. So we'll put it here. So remark, let n be a positive integer. So a collection U1, comma U2, and so on up to UK does not span, or cannot, let's say cannot span R4 when k is less than n. If your collection has less than n elements, it will not span R4. Okay, let's take a look at some function spaces. So, in particular, polynomials of degree n or less. So, examples. Determine whether the given collection of elements of P3 is a spanning set of P3. So for number 1, I have 1x, x squared, x cubed. So this time my generic elements are polynomials of degree up to 3. So let's do number 1. Can we write a generic polynomial of P3 as a linear combination of 1x, x squared, and x cubed? You might be thinking, the audience may be thinking that that is easy to do. All you have to do is, when you write your generic polynomial in P3, just take its coefficients to be the scalars of the linear combination of your elements in the set. So let me switch to the camera, to the board, and pick a generic element of P3. So let A3x cubed plus A2 x squared plus A1x plus A0 be in P3. So this is my generic element of P3. So can I write this polynomial? So can we write this fellow as a linear combination of a 1x, x squared, x cubed? And the answer is obviously yes. It is a linear combination of 1x, x squared, and x cubed. Okay, so So consequently, the set consisting of 1x, x squared, x cubed is a spanning set of P3. Okay, let's try another one. Determine whether the collection consisting of 1 plus x plus x squared plus x cubed, and x cubed is a spanning set of P3. Now this one's more interesting because it is not clear how you would choose your scalars, C1, C2, C3, and C4. Notice that there are 4 elements here, so we are going to need 4 scalars, C1, C2, C3, and C4. Okay, so let's set up and see how to deal with the question. So here is my set. So determine whether one plus x plus x squared, x squared plus x cubed spans are 4. P3, excuse me. Okay, so let's pick a generic element in the space P3. So let A3 x cubed plus A2 x squared plus A1x plus A0 be a generic element of P3. We can put a 1 here just to see that this is the coefficient of x cubed, the coefficient of x squared, the coefficient of x, and the constant term. Okay, so let's set this. So let's set this equal to a linear combination of our given 4 polynomials in P3. So C1, 1 plus x plus C2, x plus x squared plus C3, x squared plus x cubed plus C4 x cubed. Okay, so what I want to do is I want to distribute the constants and then combine like terms. Combine the constants, the x's, the x squares, and the x cubes. Okay, so let's combine the x cubes. There is C3x cubed plus C4x cubed. Okay, so take care of those two. Now let's combine the x squares. Plus, here I have C2x squared, C3x squared. Now the x's, C1x plus C2x. plus the constant term. There's only one of them, C1. Okay, so once again, this right side equals to that generic polynomial in P3. So since they are both up to degree 3, what we do is we equate the coefficients. The coefficient of x3, we equate them. The coefficient of x squared, we equate them all the way up to the constant term. So what do we end up with? We end up with C3 plus C4 equals to A3. This is now starting to look familiar. We have done something like this before. C2 plus C3. Let me reverse the order here. Put it in increasing order, sorry. So let's say C3 plus C4. And then C2 plus C3 equals to A2. So the coefficients of x squared, they're equal to each other. The coefficients of x are equal to each other. So C1 plus C2 equals A1. And then the constants are equal to each other. A0 equals A1. Excuse me. A0 equals C1. Okay, so I have to solve this system of linear equations for C1, C2, C3, and C4. Observe that this is a square system. It's a 4 by 4 square linear system. So it all boils down to determining whether the system has solutions. And for that we can use determinants, because this is going to be, the coefficient matrix is a 4 by 4, so we can use determinants here. Whenever you get square systems and you're asking for the existence of solutions, the determinant is the tool to use. Okay, so let's erase so we can make space for our coefficient matrix, to write our coefficient matrix, and then determine its find its determinant to answer our question. It might not be too difficult to compute the determinant of this coefficient matrix, because as you can see, the last row has many zeros in it. So 0, 0, 1, 1. 0, 1, 1, 0, 1, 1, 0, 0, and 1, 0, 0, 0. So we want the determinant of that coefficient matrix. Okay, let's expand along the last row. So you get 1 times the determinant of that minor. Okay, so then everything else are 0. So plus 0, minus 0 times something, plus 0 times something, plus minus 0 times something. That just drops out. We only have to worry about computing this single determinant. We learned in our study of determinants, we learned that when we exchange two rows, the determinant sign switches. So let me use that property. So this is 1 times the determinant of negative 1 times the determinant of the matrix that you obtain when you interchange first in let's do it this way. First and second row. So I'm interchanging the first and second row, so that switches the sign. Observe that we can do it again. Let's switch these two. So far I have the 1 times -1 is -1, but now I have to put another -1. This time I'm switching second and third rows. So why am I doing that? Is because I can use this pivot to eliminate that element there. But then at that point I put a -1 here that can eliminate that one. It's not the only way of doing this job, but I somehow think that is a simple thing to do. So when you eliminate that fellow right there, that's a type 3 elementary row operation. The idea to use here is that doesn't change the value of the determinant. By the way, this is just a 1, so you end up with just this, but this equals to the determinant of the matrix that you obtain when you use the elementary row operation to get rid of this, type 3. So row 2 minus row 1. 1 minus 1 is 0. 0 minus 1 is -1. 0 minus 0 is 0. I wonder if this is an efficient way of doing this problem, but at least we use some properties of determinants. I am now going to get rid of this by the same process. It's a type 3 elementary row operation, so the determinant will still be the same after we make that change. So let's see. So row 3 minus row 3 plus row 2. So 0 plus 0 is 0. 1 plus -1 is 0. 1 plus 0 is 1. I'm sorry. I'm running out of space here. Let me try to make everything visible here. Okay, so add them up. 0, 0, 1. And then everything else remains the same. Okay, I have reached a point where I can tell what my answer is. This is a upper triangular matrix, so the determinant is simply the product of the diagonal entries, which in this case is -1. So I conclude that the determinant of my coefficient matrix is going to be equal to -1, which is not 0. So that means that there is a solution to our system. We don't exactly know what that solution is. We don't know what C1 equals to C2, C3, C4, but we did determine that there is a solution, a unique solution. So we conclude that the collection in number 2 is a spanning set of P3. So naturally we're hoping to find a case where that doesn't happen. Example number 3, observe that it has 3 elements. So we're now setting up an equation that says you have a generic polynomial in P3, and you're setting it equal to a linear combination of 3 things. 1 plus x, 1 plus x plus x squared. The suspicion here should be that there is no solution to such an equation. It seems that there are not enough elements of P3 in our collection. Let me quickly set that up. Oh, it's better yet. It is not possible to write a cubic polynomial as a linear combination of 3 polynomials, all of which are of degree 2 or less. So I guess that's the fastest way of answering this question. Okay, so this is our last example. So we're asking, does the collection, so does the collection 1 plus x, 1 plus x plus x squared span P3? Answer, no, because. Now, all I have to do is think of a polynomial of degree 3. There's no way I can express it as a linear combination of those, because something as simple as x cubed. X cubed cannot be written as a linear combination of these 3. It's impossible. If I say x cubed equals c1 plus c2 1 plus x plus c3 1 plus x squared, when I combine my like terms, here's what I get. C3x squared plus c2 plus c3x plus c1 plus c2 plus c3. Here the coefficient, here the x cubed term is missing, so that has to be plus 0 x cubed. But here you have 1 x cubed, there you have 0, you conclude that 1 equals 0, which is false. So this equation will not have solutions. So the answer is no. Why? Because when you try to express the particular case x cubed as a linear combination of your given 3 elements of P3, that leads to a false condition, so it cannot be done. You cannot write linear combinations of these 3 to produce x cubed. Okay, that's all for this video. Thank you for watching.